Now we have Charles Gammie, who's going to be talking to us about black hole accretion. And Charles is a professor at University of Illinois, Urbana-Champaign in the physics and astronomy departments there. He did his PhD at Princeton, and focus of his work is on understanding black hole accretion through computer simulations in particular, understanding how plasmas accrete onto black holes and everything about that. And he is the head of for the Event Horizon Telescope, he's one of the heads of the theory working group.
One of the heads?
Yeah, one of the heads.
One of the coordinators.
So let's join me in thanking him for giving the presentation today.
Okay, thank you, Katie. Thank you very much. So my charge was to give an introduction to black holes and black hole accretion. And in the course of the talk, I'll show some EHT results. So that part of the work is presented on behalf of the Event Horizon Telescope collaboration. All right. So let me start with a picture, or 4 pictures, of a black hole accretion flow. So I know this is advertised as a picture of a black hole, but what you're actually seeing here is light, probably synchrotron radiation, from a hot plasma that is falling in, or is at least very close to a 6×10⁹ solar mass black hole. Okay, so the key points here are that it is the accretion flow that makes black holes visible. As we discussed in the first talk, we don't see electromagnetic radiation from some of the LIGO black hole mergers, perhaps because they either lack an accretion flow or the accretion flow is just too faint. It's really the accretion flow that matters here for VLBI observations, for X-ray observations of galactic nuclei, and so on. So somewhere in here, in each of these images, is a black hole. It's probably the hole in the center of this Einstein bagel. And the black hole itself, in general relativity, is characterized by a mass m and a spin a. There are no other parameters. So famously, black holes have no hair. The accretion flow itself is not fully understood yet, although I think some of the simulations we've been doing are helping to understand the accretion flow itself. At least in the models we discussed, the accretion flow is characterized by 2 key parameters. The accretion rate in grams per second onto the black hole, and the magnetic flux, phi. And I'll define that more carefully in just a moment. So I want to go through each of these parameters and talk about what they tell us about images like this. Okay, so there are our 4 parameters, mass and spin, which characterize the hole, and accretion rate and flux, which characterize the accretion flow. Okay, so let's go through these one at a time and talk about the black hole mass. So the black hole mass sets a characteristic length scale, which is gm over c squared, and a characteristic time scale, which is the light crossing time for this characteristic length scale, gm over c cubed. We know that the mass of putative black holes spans the range from 6 solar masses for stellar mass black holes in our galaxy to 10 to the 10, or I may have to revise this, 10 to the 11 solar mass black holes in the centers of external galaxies. Okay, so to be specific about this, I'm going to use M87 as an example throughout because it's of some interest. So for M87, the mass is about 6×10⁹ solar masses. The characteristic length scale, gm over c squared, is about 59 astronomical units. And the characteristic time scale, gm over c cubed, is about 8 hours. All right. So let me talk about particle motion in the gravitational field of a black hole. So I'm going to give a discussion of an effective potential treatment for motion of both particles, massive particles, and photons around black holes. So let me start and imagine that the motion of the particle is confined to a plane, and we put down a set of coordinates on that plane, which are r and theta. And then because the potential of both a non-rotating black hole and a rotating black hole in the equatorial plane of the hole, in the plane of symmetry, is azimuthally symmetric, there's a conserved angular momentum. And we can just write that at large distance is just r squared theta dot. So dot is d by dt. So this is classical mechanics 101. And then we can also characterize a gravitational field at large separation from the hole as a Newtonian gravitational potential. So that is just minus gm over r. And I'm writing here potential in units of energy per unit mass, which has dimensions of velocity squared. Okay, so again, classical mechanics 101, I can combine those and take out the motion in the theta direction and through this conserved quantity. And just think about motion in the radial direction. So as we think about this discussion, the particle or the photon is circulating around the black hole, and it's executing some motion in the radial direction. And so there's an effective potential associated with that. There's the gravitational potential, and then added to that is an effective potential which forms the centrifugal barrier. So an object with angular momentum can't get too close to r is equal to 0. And this looks like this. So I've plotted radius here with unspecified units, carefully unspecified units, and effective potential here, again, with carefully unspecified 0 and units. And this is the kind of diagram for the effective potential that one obtains when the angular momentum per unit mass, which is what this is large compared to this characteristic value, gm over c. So angular momentum per unit mass is a length, which is gm over c squared, multiplied by a characteristic velocity, which is c. Okay, so that leaves us with a characteristic angular momentum gm over c. All right, so the next step is to bring the particle in closer to the black hole and reduce the specific angular momentum and ask what happens to the effective potential. And it's possible to do this. It's an exercise in Meissner, Thorne, and Wheeler. The result looks something like this. So we've got the same two terms that we had before, but there's an additional negative term associated with the angular momentum, which is proportional to 1 over r cubed. Okay, and that produces an effective potential that looks like this. So this is for angular momentum per unit mass, which is about 4 times that characteristic value. And you'll see we've got the same minimum in the effective potential. We have circular orbits that sit here at the bottom of the minimum. We have, for an eccentric orbit, the particle will execute nearly harmonic motion around the minimum in the potential. And as we get closer to the black hole, the shape of this minimum changes a little bit. And that change in the shape of the minimum is what produces the precession of the perihelion of Mercury. Because it means that the characteristic radial frequency is no longer equal to the characteristic circular frequency. Okay, but then in addition to that, we have this maximum and then a pit in the potential at the interior. And that's really the central new feature of the effective potential for a black hole. And I've written this for a non-rotating black hole, by the way. So for a spinning black hole with spin factor A greater than 0, this becomes a somewhat more complicated equation that would sort of run off the edge of the slide here. All right, now let's ask what happens as we turn down the angular momentum even more and the shape of this potential changes yet again. So I've reduced it by 0.5. And now the shape of the potential looks like this. So I don't have perfect expertise with keynote line drawing, but there's supposed to be an inflection point there. So a 0 in the derivative, and things come in and then go down in that 0 in the derivative. So there's a circular orbit here, but it's not a stable circular orbit. So this is the innermost stable circular orbit. And this is another key feature of motion around black holes in general relativity. And for a non-rotating black hole, this is located at 6 GM over c squared, where again, GM over c squared is this characteristic scale. And for a non-rotating hole, 2 GM over c squared is the Schwarzschild radius, or the size of the event horizon. Okay, so yes, so I've also put the event horizon in there at 2 GM over c squared. Okay, so this is a brief description of motion around a black hole. We've got a series of circular orbits that exist into an innermost stable circular orbit. And we think that inside that point, material begins to, plasma, if there is plasma around the black hole, begins to free fall in toward the event horizon. Okay, so next, let me go and ask what happens to this effective potential if we consider the motion of photons rather than massive particles. And in that case, we obtain an expression that looks like this. And now effective potential just has a single maximum. And that means that there is a circular orbit around the black hole for a photon, and it's right here at 3 GM over c squared. If we sit on that point, it's obviously unstable because the second derivative here is negative. So if we're close to the photon orbit, we roll away either toward the inside where we escape to large radius, or toward the outside where we escape to large radius, or toward the inside where the photon falls into the event horizon. Okay, so in the course of modeling event horizon telescope results, we build models in which there's a luminous plasma that fills this volume around the black hole and generates photons by the synchrotron process. And some of those photons wind up close to the photon orbit. They're born close to the photon orbit. And the question is, what happens to those photons? What's the fate of those photons that are born near the photon orbit? Okay, well, the geometry of the situation looks, well, actually, let me anticipate this a little bit by saying, well, we're born near the photon orbit. Let's imagine that we're just a little bit outside. So we make several circuits around the black hole and then roll away toward large distance. Okay, so those trajectories look something like this. So here's the photon is born somewhere in here and then circulates around the hole. It's really hard to make a photon that circulates so precisely around the hole, as several people here have spent a great deal of time understanding. But eventually the photon rolls away and goes toward infinity. And it turns out that at large distance, it makes an impact parameter with a line of sight that goes toward the center of the black hole that's calculable, that's analytic, and it's root 27 GM over c squared. So photons that come off this photon orbit wind up on the sky in a ring around the black hole at that impact parameter of root 27 GM over c squared. Okay, so let's just project that onto the sky and ask what it looks like. So let's imagine we have a black hole that's at some large distance d away from us, and that gives us a characteristic angular scale, which is the gravitational radius divided by the distance, which for M87 is something like 3.8 microarc seconds. And let's just naively project what a non-rotating black hole looks like onto the sky. So it's 2 GM over c squared in size, We just put it out there and project it onto the sky, and there it is. It's black. Okay, so that's the event horizon at 2gm over c squared, 2gm over c squared d. And put this over here. And now let's take the photon orbit, which is at 3gm over c squared d, and naively, again, project that onto the sky. So we're not doing any radiative transfer. We're not tracking the photon orbits as they come toward us. We're just taking r over d to get the approximate angle. And that's, again, at 3gm over c squared d. OK, so now let's project this characteristic impact parameter, root 27 gm over c squared d, onto the sky. And that gives us this circle here. It's substantially larger than the black hole. And again, at root 27 gm over c squared d. So the way you should think of this is if I track back a photon that appears in my detector here, then that photon originated outside the photon orbit, whereas every line of sight that I track back toward the black hole here winds up at the event horizon. And this is the critical curve that divides photons that wind up on the event horizon from those that bypass the black hole and come to us. Okay, so this is just an example of strong gravitational lensing used in a way that is not exactly the way that extragalactic astronomers use it. There should be another term for this, like really, really strong gravitational lensing. Okay, so that's the basics on orbits around black holes. There is an innermost stable circular orbit, which actually projects onto the sky out here. There's the event horizon at 2gm over c squared for a non-rotating black hole, photon ring, this critical curve. Okay, so now let me go on to black hole spin. And black hole spin is defined as the angular momentum content of the black hole, which I'll denote J. And I apologize for this abuse of notation. A is supposed to be reserved for something that's dimensional, but not everybody's perfect. So it's the angular momentum divided by the characteristic angular momentum for the black hole. So characteristic angular momentum per unit mass, gm over c, multiplied by the mass of the hole gives you a characteristic angular momentum for the hole. And in general relativity, it's possible to solve Einstein's equations under the assumption of an axisymmetric, asymptotically flat metric. And in that case, one finds a series of solutions with A varying between -1 and 1. It's perfectly possible to write down a metric with A outside this interval, but there's severe theoretical prejudice against those objects. So it's actually very hard, we think, to get past A of 1 to spin something up. And there are also exposed singularities out here. So we tend to think of A in general relativity as lying between -1 and 1. So spin is the famous second parameter for black holes, and it's very hard to measure. So there are efforts to measure spin from stellar mass black hole binaries using either iron lines or fitting of the X-ray emission from the accretion disk, and I think those are pioneering efforts, but we're not sure that we understand all the systematic errors associated with those yet. So in M87, there was an effort to see what we could say about spin in the course of modeling the EHT results. And I would say that models with spin greater than 0 are consistent with the data for reasons that I'll mention later on. Mainly this has to do with objects which are non-spinning not being able to produce an energetic jet. Okay, so there are the two black hole parameters. They're sort of independent of the accretion flow parameters. It's worth saying out loud that the accretion flow in both stellar mass X-ray binaries and in extragalactic supermassive black holes is likely to be very, very, very much less massive than the black hole itself. So we can think of the accretion flow as really just moving in the gravitational field of the black hole. Okay, so on to the next parameter, which is the accretion rate. One reason that the accretion rate is important is because we think that the luminosity L of the accretion flow is related to the rate at which matter is falling onto the black hole. You can't stop me from writing that the luminosity is equal to the accretion rate, m dot, grams per second, multiplied by the energy per unit mass liberated from the plasma radiatively as it falls in toward the black hole. And you can't stop me from doing that because I've also put this epsilon in front, which takes care of all your questions about what fraction of the rest mass energy is liberated. So there's a classical model of accretion called the thin accretion disk, which we think very definitely does not apply to EHT sources, which says that this epsilon is directly related to the spin, and it's related to the binding energy of particles on the innermost stable circular orbit. And that classical theory says that this epsilon varies from about 6 and a bit percent for a non-rotating black hole, all the way up to 42% for a maximally rotating black hole, reaching 10% or 0.1 at values, sort of reasonable values of 0.9 or 0.95 for the spin. Okay, so the accretion rate governs the luminosity of the flow. And there's a characteristic accretion rate. Actually, I've screwed this up. This should be the Eddington rate. But it's, sorry, the Eddington luminosity. But the Eddington luminosity is related to the accretion rate through this equation. So anyway, replace that by L. And this is a characteristic luminosity at which, as Kelly said, the radiative force from the accreting plasma can overcome the gravitational force of the black hole. And this is sort of a characteristic luminosity, or through this equation, accretion rate, at which radiation begins to become important for the structure and evolution of the black hole. So when one gets close to the Eddington limit, to the Eddington rate, one has to include radiative effects, cooling, and radiation forces. Okay, so for M87, again, the Eddington accretion rate is 1 over the fine structure constant in units of solar masses per year. And we think that the accretion rate is, the actual accretion rate at the time of the EHT observations is about 10 to the minus 5 of that. So something like 10 to the minus 2 solar masses per year. 10 Jupiters. Okay, so that's it for accretion rate. Now I want to go on to magnetic flux. And every time I bring this up at an EHT meeting, people kind of look at me like, you know, this doesn't seem that interesting to us, Charles. But I want to first say what this is and then say why it's important. Here's a cross-section of a black hole that's accreting matter onto the black hole through an equatorial disk. So let's say the axis of symmetry is here, and this stuff here, the orange, is the hot plasma in official EHT colors that's orbiting around the black hole. And what we want to measure here is how much magnetic flux is trapped in the black hole. And we do that by taking an integral over one hemisphere of the black hole. So we take integral of dA dot b. So this is not exactly what's going on, but I think you get the idea. And it turns out that there's a characteristic value for this, this flux, which is related to the accretion rate. So you can ask, at what point does the ram pressure from the accretion balance the magnetic pressure from the magnetic field that's trapped inside the black hole? And that simple estimate gives you this value for the characteristic accretion rate. Sorry, for the characteristic magnetic flux. All right, so, so the way this is described in the accretion community is that solutions, accretion flows with subcritical magnetic flux are described as SANE, which stands for standard and normal evolution. So this is, I give full credit to Ramesh Narayan for this terminology. And those with the maximum possible value of the magnetic flux, which is the value where the field begins to push aside the accretion flow and escape from the black hole. Those models are called MAD models, for a magnetically arrested disk. And there are a lot of people who have worked on variations of this model, including Dave Meyer, who's here somewhere. This is usually cited as the point of origin for this, for these MAD models. Okay, so now I've covered the four basic parameters, or what I claim are the four basic parameters. Now let's talk about models. And this is a figure from one of the EHT papers. The actual data is over here on the left. One of our simulations, and I'll say more about where this comes from in a moment, is shown in the middle. So we can easily get much higher angular resolution than EHT, and then we can blur it to the resolution of EHT. And you can see that these models more or less look like each other. It turns out that the flow is highly turbulent, and so we never expect the models to look exactly like the data, but they're pretty close. So we've got the dip in the middle. We have an asymmetric donut of emission around at the photon ring in both cases. Okay, so what goes into these models? These models that work pretty well and are in fact exactly the models one would have constructed before the EHT data came in. And in fact, people like Jason Dexter and Monika Mashka-Brushka actually did make models like this before EHT. Okay, so so to make an image like that, we need a model, a dynamical model for the inflowing plasma. And I'm going to show you an animation here in a minute, but let me just say before I start it what this is. So on this side, we've taken a section in the poloidal plane of the accretion flow. So this stuff here is orbiting the black hole in and out of the board. The black hole is right there. Here, we've taken a cut through the equatorial plane of the accretion flow. And the color here shows the, it actually shows the log, I think, of the rest mass density. Okay, so that's rest mass density in the frame of the plasma. Okay, so things take a little time to get going. You'll see that there's a little bit of activity that develops. This is a result of the interaction of the magnetic fields with the orbiting plasma. And this produces accretion. So matter that was out here and was kept out here by its angular momentum begins to lose angular momentum and accrete onto the black hole. Okay, and you can see here that the structures that are produced inside the accretion flow are quite non-axisymmetric. So this, I can now talk about this because we went through the exercise at the beginning of just describing the parameters. This is a model with a spin 0.94 black hole. It's a non-radiative simulation, so that that implies that we have to be somewhere way below the Eddington rate. We don't know exactly where. And this is a MAD model. So this model is trapping flux inside the black hole. And these events that you can see over here consist of flux escaping from the black hole into the accretion disk. Okay, so this is a numerical model. It's a general relativistic Magneto-hydrodynamic model. What this is just a fluid integration in an exotic context. So numerical fluid models are used throughout astrophysics. We've built one in an exotic context. So we've written the fluid equations in covariant form, and the fluid equations just express conservation laws. So conservation of particle number, energy, and momentum. So that's always a good place to start. And this is a magnetized fluid model in which the field lines are dragged with the accreting plasma. Okay. So these guys are three-dimensional and time-dependent. The integration is done in a particular set of coordinates. So you always have to worry about coordinates when you describe a black hole. And this uses so-called Kerr-Schilg coordinates, which allow us to extend the domain of evolution into the black hole. So we can watch material falling through the event horizon. And we don't have to worry about imposing a boundary condition at the event horizon, which has been with more commonly used Boyer-Lindquist coordinates, has been a topic of inexhaustible controversy. Okay, this is, these models can be described in some average sense using phenomenological, time-independent, axisymmetric models. But one of the key features of these that can't be captured, as far as we know, in those phenomenological models is the turbulent fluctuations. And it turns out that those are important for understanding EHT results. Okay, we integrated that model there using a code called HARM, which is our local Illinois code, but we've done an exhaustive comparison of all the codes on the market for doing this. So Oliver Porth at Amsterdam led a comparison project, and these generally produce consistent results. So we think we're correctly integrating the equations that we set out to integrate. Okay, so inevitably, models like this have weaknesses. So let me talk about what's going on inside the sausage factory. So first of all, these are ILS simulations. So ILS stands for implicit large eddy simulations. So they have no explicit treatment of dissipation. There's no viscosity, there's no resistivity to diffuse the magnetic field, and there's no heat conduction. So all that is handled by the numerical closure model. And this is a source of possible concern. Another concern is that the plasma is actually collisionless. So the matter around M87 probably has a density of around 10 to the 4 electrons per cubic centimeter, a magnetic field strength of a few tens of Gauss, and a temperature of somewhere between 1 billion and 1 trillion Kelvin. So it's a really hot plasma, and that means that the mean free path to Coulomb scattering for the electrons and ions in this plasma are long. And in fact, they're much larger than this characteristic scale GM over C squared. So this is a fully collisionless plasma. And collisionless plasmas have many degrees of freedom. They are not readily described as a fluid. And so we're taking the bold step of describing them using a fluid model, which is probably not a bad place to start, but it's not the end of the story. So conserving mass, momentum, and energy is a good place to start. Okay, I see I'm in overtime. Okay, so the initial conditions are artificial. Radiation is not included in these simulations, and it may be marginally important in M87. And I'm looking at Avery over there to mention that pair production physics is also not included. So one of the sources potential sources of radiating leptons is not included in this particular set of models. Okay, so how far along am I? Okay. When we run these models, we see outflows along the poles. And the outflows are due to magnetic field lines that come down from large distance and then go through the event horizon of a rotating black hole. And the field lines are dragged by the black hole as it rotates. And this is known as the Blandford-Znayak effect. Okay, so it's long been known that rotating black holes have a free energy associated with rotation. This is noticed by Penrose in the late 60s. And Penrose proposed a process for getting the energy out using particles, which Press and Tucholsky showed is unlikely to be applicable in an astrophysical setting. But then Blandford-Znayak came along in the late 70s and showed that you could build what is essentially a pulsar model for the wind over the poles of the black holes, and you could get this energy out. And there's nothing particularly mysterious about this. It's much like the spin down of a rotating star by field lines that are attached to material at larger radius. Okay, so we know that happens in nature. With a spinning black hole, we have a spinning object in the middle, and field lines connect it to plasma at large distance and can break it, getting energy out. Okay, so this is known to produce a collimated pulsar-like wind. So pulsar-like in the sense that the density is extremely low and it's magnetically dominated. The energy density of the magnetic field is large compared to the rest mass energy density of the plasma. So we can link the luminosity associated with this process to the flux on the black hole. If the flux is small, you get nothing out. If the flux is larger, you can get a substantial fraction of the rest mass accretion energy, rest mass accretion luminosity out. And it depends on spin, at low spin as the square of the spin parameter. So one needs a spinning black hole for this to work. Okay, so again, the GRA-MHD models show Blandford-Znayak-like jets for spin greater than 0. And I think that one of the big questions for Event Horizon Telescope and maybe space-assisted VLBI in the future is, can we track the plasma that's on field lines that are attached to the black hole or to the accretion disk and verify directly that Blandford-Znayak is occurring? So those two pieces of plasma will rotate at different rates. The stuff that's attached to the black hole rotates with the rotation frequency of the hole. I feel like I'm George Bush when I do this. I don't know if anybody's young and old enough to get that, but George H.W. Bush. And the stuff that's attached to the disk will rotate more slowly. And it may be possible to actually see that. Okay, I'm in double overtime now. So let me just show you what happens when you take one of those GRA-MHD models and create an image of it. So here we built the same, we've imaged the same model that I described before. What you're seeing is synchrotron emissions, so relativistic electrons spiraling in this 10 Gauss magnetic field around the black hole. You can see the photon ring here, and you can see turbulence in the flow producing fluctuations in the surface brightness around the ring. Okay, so let me just quickly say what goes into this. So this is a covariant polarized radiative transfer model. So we just integrate the equation of radiative transfer. We have codes in the collaboration for doing this, and we know they're convergent. So there's a paper coming out by Roman Gold about this. And we know that if we know what the distribution of electrons over Lorentz factor is, the electron distribution function, then we can calculate the transfer coefficients, the radiative transfer coefficients, the emission, absorption, and Faraday rotation coefficients essentially exactly. So there's really no approximations that go in here once the electron distribution function is specified. Okay, so here's what's inside the sausage factory. I think this is what I was asked to talk about. I'm getting to it at the end. So this is done as a post-processing step. So the radiation is not now included in the evolution, although there are limited examples of people doing that. We assume an electron distribution function or parameterize it and then look for the best fit parameter. And we use something called a fast light approximation, which I'll describe in questions if anyone wants to know more about that. So here are the main points. So it's accretion flows really that make black holes visible. There are 4 key parameters. Strong gravitational lensing helps us out. It makes these things larger on the sky and produces this photon ring. We have dynamical models of the accretion flow, and those produce jets that in the simulations are powered by the Blandford-Znayak process. And then we can couple these to radiative transfer models and roughly reproduce the Event Horizon Telescope results. So that's it. Thank you.